Good evening. Welcome to the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m. already, but participants are yet to join. So we'll wait for a few more minutes before we start. Thank you. Good evening and welcome to the live sessions for the course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a faculty member in the Department of Mechanical Engineering at IIT Guwahati. And I am Sourav Goswami. I'm a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. Uh, Over the last few weeks, we have been looking at advanced additive manufacturing processes, and precisely we looked at the wire-based additive manufacturing processes, both with laser and beam type, both with laser and arc type uh, energy sources. And we also started discussing about the powder-based additive manufacturing processes. And first, we would be talking about the powder feeding based or the blown powder based additive manufacturing processes. Also, in the subsequent weeks, we'll be looking at processes that are similar to what we typically called as a powder bed based process. That again will have say different energy sources such as whether it's an electron beam or a laser beam, and whether we are melting the powders fully, we are taking it, heating it enough to cross the melting temperature, whether we are just sintering it, which is say, typically done at some 80% of the melting temperature. We're also talking about the various process subsystems for powder feed-based additive manufacturing processes. We looked at the different nozzle designs, the role of carrier gas, and how the coaxial nozzles, the side feeding nozzles, or whether the energy source is coming from the center and the powder is coming from the sides, or whether the powder is coming from the center, energy is coming from the sides, whether that powder energy stream is discretized into say two or three different channels, or whether it is one continuous coaxial source of feeding. All of these things affect the deposition characteristics. And today we'll continue discussing about such things. Also, we'll talk about some uh, simplified modeling for the powder-based additive manufacturing process. So let us start. We were last discussing about discrete coaxial nozzles. That is, you have multiple nozzles around the sides, which feed the powder into your region of interest where you want deposition to happen. And if I can just find the correct color, yeah, here it is. Say here, and your energy source, that is the laser in this case, is coming from the center. So discrete coaxial nozzles use multiple, say typically 3 to 4 jets of powder stream delivering feedstock directly to the melt pool via separate and distinct powder delivery channels. And the reason for this is to overcome the lack of omnidirectionality that we had encountered for some of the processes. Now, by increasing the number of these discrete nozzles, say from 3 to 4, maybe you can also go up to 6, say, what you can do is A, control the flow of powder better. B, you may also be able to deposit a larger volume of powder per unit time because now you have multiple nozzles. You can feed powder at, say, a decent feeding rate through all the nozzles, and thus you can deposit more powder per unit time. You are also able to, say, better control and actuate the composition of the powders. As in, you may be able, if you want to build functionally graded materials, or in cases where you say want to develop new alloys for additive manufacturing, you want to alloy powders on the fly, say rather than pre-mixing them via some process such as ball milling or planetary energy milling. Rather, you can have separate reservoirs of powders, and you want to mill them, you want to mix them and alloy them on the fly. That is, while they are being fed into the melt pool. Then you can use these various nozzles to feed different material powders of different materials, and you can even engineer these new alloys. So they are really flexible, and they further enhance the capabilities of such powder be feed-based AM processes. The integration of these channels with respect to each other affects powder flow characteristics and shifts the location of the powder stream's focal point relative to the laser beam. And we'll look at how that happens. This may happen both across the plane of deposition and along the plane of deposition. What this means is, say, if this, for some layer, if this is the plane in which we want to deposit our powder, Now, by changing the relative angles between these nozzles, say for one case, case 1, they might have been inclined like this. Say for some other case, case 2, they might have been inclined differently. So now we are seeing that, and there will be some intermediate case where the focus is on this layer on the plane itself. So we can have variation across this plane of deposition. That is, in one case we have the focus is above the plane of deposition, in the other case it is below the plane, and this is the optimum in between. And in for this optimum height as well, that is in the same plane, there can be a lack of directionality, omnidirectionality. While we deposit at different regions, say whether we deposit, if this is our laser head, whether we are depositing directly under it or say at a small angle, or whether we are deflecting it to a far field region, can affect the powder deposition characteristics. The number of powder streams or channels that are participating in deposition has a significant influence on stream characteristics and further on the catchment efficiency. What this is, we'll also be looking at, but essentially what it means is we are feeding a given amount or a controlled amount of powder into the melt pool, but it is not necessary that all of that powder that we are feeding will end up forming the deposited bead. Some of that powder is lost. In fact, there was a time not very long ago when most of that powder was lost. And this efficiency actually measures the efficiency of the system, how much wastage we are preventing, and it also helps us calculate what is will be the actual height of each layer that we are building, whether it is commensurate to the amount of powder that we are supplying. Because one engineer might think that I am supplying some controlled quantity of powder per unit time. The bead that I am getting, subject to certain approximations, should also have a certain profile, say we assume parabolic or elliptical in our cases, and correspondingly it should have some given height. But after the printing process, we find that the printed part is far, far smaller than the design geometry. So such discrepancies can arise based on catchment efficiency considerations. Also, several studies have shown that with the increase in the number of powder channels from 3 to 6, the particle velocity in each of these delivery streams reduce. One reason I can think of is maybe because of collisions between the powder particles, which may retard them and prevent them from spreading too far wide. And with the reduction in particle velocity, an increased clad area, that is, if you are looking at the cross section, then an increased build area for the bead. So maybe something like this, signifying higher catchment efficiency for other process parameters remaining constant was observed. So the powder mass concentration or the amount of powder. So here it is defined as the number of particles per unit area of the focal spot is negatively correlated to nozzle exit diameter dn and injection radius rn. A negative correlation implies, say if this powder mass concentration is some Cp, for instance, negative correlation implies inverse proportionality. So 1 by dn, nozzle exit diameter, and injection radius. So 1 by RIN. Similarly, the standoff distance, which we know is defined as the distance between the nozzle and our focal point, or in cases where the focal point is on the substrate itself, then the distance between the nozzle and the substrate of the build plate also shows a negative correlation with the injection angle phi and the nozzle exit diameter dn. So SD is inversely proportional to phi, and maybe I can write that better. And SD is also inversely proportional to dn. An increase in either of these quantities decreases the standoff distance and moves the focal plane closer to the nozzle exit plane. And previously we have discussed how this may not really be desirable, because when we are moving the focal plane of the powders closer to the nozzle, there is a chance that Now, a larger number of particles which may bounce back from the surface, or a greater quantity of the fumes that may be generated during the deposition of these particles, are now in closer proximity to the nozzle, and thus also in closer proximity to the laser optics, and they can enter the head and end up, uh, say, maybe covering the laser optics in soot, or maybe end up harming the optics in any other way because they're very fragile, and so this becomes undesirable. Also, the deposition characteristics themselves have been optimized and have been tuned for a fixed standoff distance. Of course, with each layer the standoff distance varies, and that is why previously we also looked at some fundamental modeling of how the build height layers are changing with the change in the substrate geometry to ensure that we are able to maintain a reasonably constant standoff distance, because it is important to maintain isotropic behavior. Of course, there will be some variations because the deposition is not really, say, flat. There will be some non-uniformities. You will never have a scenario where, say, this is the build plate and your deposited geometry is exactly flat and straight. More typically, what you'll end up having is some undulations because of process instability. So it will be higher at the corners, and even in between it need not be flat. There can be some small undulations and something like this. But what you need is to be reasonably, have a reasonable approximation of the standoff distance. Now the injection radius Rn is positively related to standoff distance. That is, Rin is directly proportional to SD. An increase in Rin increases the standoff distance. Okay, then maybe we should write it the other way. SD is directly proportional to RIN because an increase in RIN increases the standoff distance. Now, there are several design considerations when we are designing such powder feed based additive manufacturing process, or in certain cases, when we are trying to design some new nozzle which may provide some additional functionality over the prevalent types. Now, ensuring the area of overlapping powder streams is more than the laser spot size ensures the uniformity of the deposited tracks. So here we have two cases. I will just enlarge this image for easier visualization. So in this first case here, we have these powder streams. So the ellipses are the streams are powder. They're elliptical because while the powder stream may be circular, the channel may have a circular cross section. Because of the inclination of the channel with the flat substrate or build plate, the projection that we get on the substrate is elliptical. So this is the entire powder channel, and you have a powder footprint, and you have four of them. And then there are these overlapping regions. So these are regions one, that is only one stream is coming in there. Such an overlapping region, such as shown by purple in our case, is two because you have two powder streams overlapping. Then there are these regions where three powder streams are overlapping, which I am showing in green. And finally, the central region, which I will highlight, has overlap from all the four powders. So that is the region of maximum concentration. Again, the diameter of our laser is highlighted in orange, and we see that the concentration of powder is changing within the laser spot. Also, if we were to move along any of these directions, say if along direction A or along direction B, then we see that the type of feeding is changing because we do not have equal feeding or equal concentration of powder in all directions. This may lead to the problem of a lack of uh, omnidirectionality, isotropic properties. Whereas in the second case, where the overlap region is larger than your uh, laser spot size, irrespective of the direction you might want to move in, whether it be along direction A, some intermediate direction B, or along the horizontal again, we see that Because the overlap region of the powder streams is so large, omnidirectionality is maintained, and thus we can expect reasonably isotropic properties irrespective of the direction along which we are scanning. Ensuring the area of overlap powder streams is more than the laser spot size, the area of overlapping powder streams is more than the laser spot size, ensures uniformity of the deposited tracks. This also highlights the importance of achieving a proper and optimum standoff distance from the substrate. As we just saw, changes in the standoff distance can change the powder deposition characteristics and will induce a corresponding change in the overlapping area of the powder streams. So depending on whether the angles are changing or whether the standoff distance is changing, we can expect that the nature of this overlap will also be affected. Improper standoff distance can not only lead to reduced catchment efficiency, but can also affect the track properties. Now, as we were discussing, if someone would want to fabricate a functionally graded material, FGM is functionally graded material, one can definitely use such a powder feed based additive manufacturing process. And the amount of literature on FGMs across the build direction, that is in the deposition plane, is far more limited than along the build direction, that is perpendicular to the deposition plane. So what is being said is, along this bead or in this plane of deposition, controlling the composition precisely is very difficult. Whereas when we are moving along the build direction, that is in most cases along the Z direction, because of the change in step over height, change in layer height, because of say the time delay between building one layer and the next, often we get ample time to modify or change the uh, powder composition or the material should it be needed. And thus it's very easy or relatively easier to achieve functionally graded materials along the build direction. And here we have an example where we have four powder streams and together they constitute a discrete coaxial nozzle. Stream 1 and 2 deliver copper to the left side of the pool. Stream and whereas channels 3 and 4 deliver tool steel to the right. And if such a configuration were to be used, you would find that towards the bottom you have this grayish region going all along, which is rich in tool steel. And for this section towards the other side, you have this almost orangish section, which is rich in copper. And in between, you'll have some intermediate composition. So there is some, even per bead, there is some preferred gradient of composition, which might not always be desirable. And how we can overcome, say, such uh, an anisotropy in composition is maybe we can have copper being say deposited from nozzles 1 and 3 and steel being deposited from nozzles 2 and 4 to ensure that we have both powders on both sides. Or what we can have is maybe if the head can constantly rotate, then the powders can also be constantly rotating and thus the material can be isotropic. But again, everything depends on the type of application that you are trying to achieve. Now, as we just saw, since we cannot realistically have support structure in the case of metal AM, because removing them become quite the task. Typically, we avoid support structures altogether in the case of simple prismatic geometries, or in the case where we might have overhangs or complicated geometry. Excuse me. In the cases where we have overhangs or complicated geometries, either we use a table with more degrees of freedom or higher number of degrees of freedom, something like say a 5-axis table, or we can use a high degree of freedom robot, a robotic arm which will have say some 6 degrees of freedom. And again, each of them have their own advantages and disadvantages. But essentially what is happening in either cases, we are trying to remain normal to the slicing plane that we are now trying to deposit. And in this case, the head will tilt. Because of this tilt and because of the action of gravity, the powder which gets jetted out of this deposition head will not be uniform, as is shown here. Because of the action of gravity, there is a higher concentration of powder towards the bottom, whereas in this upper region, there is a deficiency of powders. And thus, a head tilt renders continuous coaxial nozzle non-omnidirectional. Advantage of the discrete coaxial nozzle over a continuous one is the ability to manipulate carrier gas flow rates and flow velocities for individual powder streams. A head tilt of continuous coaxial nozzle, typically over an angle of 45 degrees, renders it non-omnidirectional, with increased density of powder on the bottom than towards the top. With discrete coaxial nozzles, omnidirectionality even beyond 45 degrees can be easily restored by simply increasing the drag velocity of carrier gases for, say, stream 3 in this case, compared to the others like 1 and 2. There are also energy-based considerations, such as for this case shown here. This powder particle A, which is coming from one periphery of the powder jet, will be among the first of its lane to encounter the laser beam, and then as it travels through the laser beam, it will continue to absorb some amount of energy, and eventually it will go into the melt pool and get deposited. So particle marked A on its path towards the center of the melt pool interacts with the laser beam at location X, as we just saw. From X onwards, particle A strips a portion of the laser's energy and directs it toward the center of the melt pool where it is headed. This, combined with the typically Gaussian heat and intensity profile of the laser beam, results in insufficient heating at the edge of the melt pool and excessive heating at the center. Consequently, the track so generated shows a lack of fusion with the substrate at the edges and excessive dilution towards the center, as we can typically see here. So not only is the energy density higher in the center, and remember we are just looking at one cross section, so if you look at the 3D space or we look in the top view, it will say decrease as we go radially outwards. Because of this high energy, already we have more energy input or more energy intensity near the center. Further, because of the interaction of particles such as the one that we are seeing at positions A and X, this also takes away energy from the peripheries of the laser beam and deposits it near the center. Essentially, what this culminates in is this typical profile where the melt pool is narrow near the edges and deeper near the center. Also, with changing energy densities, the mode of this deposition will also change. So typically this has been borrowed from welding. And if you have a very high energy density, you may also end up with something called a keyhole, where your melt pool can become very deep, or when you are in conduction mode, your melt pool will be more or less similar to what you see here. So not very deep and having good bonding between the deposited bead and the substrate. And while keyhole may appear to be, in some cases useful because you're getting a lot of dilution, what it can end up doing is if you have a thin feature or if you have an overhanging feature, because of the depth of this keyhole, that entire feature can be destroyed because it will go all the way through that feature. Secondly, these keyholes typically result in large pores, which tend to weaken your structures. So they are undesirable for in most circumstances. Consequently, the tracks so generated show a lack of fusion with the substrate at the edges and excessive dilution at the center, as we just saw. Now, one more advantage of using a central feed powder delivery nozzle is the minimum divergence of the powder stream. In the case of coaxial nozzle, the recorded efficiency can be as low as 30%, whereas for central feed nozzles, that is the powder is coming from the center, whereas laser is coming from all the sides. The efficiency is easily above 80%, which is significantly better. In the laser-based active deposition setup that we have here in our lab at IIT Bombay, we have a wired EED setup, which also has a centrally fed wire. In fact, it has dual wire capabilities, and the energy source is in the form of discrete coaxial lasers. So you have 6 discrete coaxial laser beams coming from all the sides, and that also ensures that we have a very high catchment efficiency. Either way, for wire, the catchment efficiency will always be very high because you don't have these powder particles um, which can bounce off or other effects. But also this ensures the omnidirectionality of the process because typically for other processes you have the wire being fed from a side. Also, based on the energy profile or the laser beam energy intensity distribution, you may end up having different types of deposition characteristics, such as shown here. Here we have this ring type of energy distribution or donut type. Here you see these two peaks along a cross section. So this intensity is more like say along one such line, and you are trying to see how the peaks are. Then top hat, where then there is the energy is more diffuse, so even in the center you have a larger amount of energy compared to this case where it was nearly zero. So this is top hat minus. Then you have a top hat plus, and these names are actually coming from this deposition. So this looks like a hat. In one case, the hat is like this. And for top hat plus, it is something like this, and so on. And then there's the Gaussian-like deposition that we see in the last frame. And we see for each of the cases the type of bead that is forming. For ring, it is pretty shallow, whereas for the top hat configuration, it tends to be say deeper. And then you have the Gaussian-like deposition bead that you commonly encounter. Now, while discussing these beam-based, uh, wire-based processes, there was a question during the assignments that during our practice sessions where we saw how we cannot really have a blown powder or gas-based setup with an electron energy beam uh, source, and that is because of the need to maintain vacuum. This has also been recognized, and thus some non-pneumatic nozzles have also been proposed. And let us see what is the need and how they compare with your typical conventional pneumatic nozzle. So the high particle velocity leads to a decrease in powder catchment efficiency along with deteriorated surface finish of the deposited clad. The use of conveyance and shield gases increases convective cooling of the melt pool, thereby creating high energy dispersion. Powder particles traveling with high velocities, upon impacting the free surface of the melt pool, generate a force of sufficiently high magnitude, and the resulting track often shows high dilution in the center and a lack of fusion at the edges. Studies have also suggested that the entrapment of carrier gas into the melt pool, which leads to increased porosity and consequently a decline in mechanical properties of as-built parts. This is also something we discussed during the problem-solving exercise last week. And here there is a comparison for pneumatic and non-pneumatic powder delivery nozzles. We see that for the non-pneumatic case, the deposited cross-section was significantly higher. The porosity was also reduced by a great extent, and the surface roughness is one magnitude, order of magnitude less. So this would present a very rosy picture, suggesting that non-pneumatic nozzles should be the industry standard rather than these gas-assisted nozzles. However, we are yet to see any non-pneumatic nozzle being put to use in a commercial machine because often, while proposing the technology is easy, translating it into a commercial machine and qualifying it can take a lot of time, and there might be other challenges which we are not, which we have not encountered yet. However, for the sake of academic interest, a few such systems have been described here. And Professor Kapil also mentioned that most of these methods do not maintain a concentric laser beam, although such a configuration can be devised. So there is ample scope in this field if some of you might be interested to research and develop such technologies further. So in the first case, we have this torsional vibration applied to an offset piezoelectric. So this piezoelectric is offset from the center. Because of this eccentricity, any longitudinal vibration of the piezoelectric leads to a torsional vibration in this embedded powder filled glass tube. And here you have the die of the tube between 50 and 125 microns. The powder particle size for copper, iron, and invar is between 3 and 22 microns, which is a very tightly controlled distribution. The frequencies that you typically use in such a case is close to 50 kilohertz, 49 kilohertz to be exact. And the powder deposition rates are anywhere between 0.005 to zero point 0.3 milligram per second. So uh, that is something to think about. For the powder flow actuated by a ring type piezoelectric, in this case you have rather than a simple say prismatic piezoelectric, now this is in the shape of a ring, which is giving some torsional vibration to the powder ring. Here the tube diameter is between 110 to 400 micrometer, so it is around 4 times larger than the previous case. The particle size also is far greater, between 14 and 72 micrometer, which is a more realistic powder distribution. The frequency has not been explicitly stated, but the powder diffusion rates can be as high as 10 to 30 milligram per second. So again, one order of magnitude higher than the previous case. Then there are these other designs where they use a bath in conjunction with a sonotrode, and the vibration travels through the water bath to the powder and helps in its delivery. Here the tube is even wider at 280 microns. The powder particles are very small at 12 microns, and there's a pulsed vibration of 20 kilohertz, and the powder delivery is again 0.05 milligram per pulse. Then you can also use some acoustic vibration rather than ultrasonic vibrations, and this can be transmitted via subwoofers. Here the tubes are very wide at 380 to 600 microns. The powder particle size can be as high as 212 microns for copper and S13 tool steel. The frequency is between 50 and 300 hertz, and the powder deposition rates are between 5.8 to 35 milligrams per second. You also have a combination of horizontal and vertical piezoelectrics, which can give you powder deposition in the range of 1.25 to 5.80 milligrams per second, again at ultrasonic frequencies of 20 kilohertz. And finally, you have this concentric laser beam and powder feed mechanism, where again there is a central piezoelectric, most probably a ring type, and a powder hopper, which feeds the powders through these three flow channels that we can see. And for this case, the mass deposition rate is as high as 120 milligram per second. So as you can see, along around say one order of magnitude higher than the ones we previously encountered. And again, it uses an ultrasonic frequency of 20 kilohertz. And to summarize, here are how the common design parameters and process parameters affect the deposition characteristics. For the power injection angle, a low power injection angle will support a longer depth of focus, consequently promoting an increased range of passive stability and high deposition efficiency. So, low is preferable. A high mass flow rate is often associated with increased surface roughness and track porosity, but then if you have a too low mass flow rate, your build time will be very high. Also, the as we saw in the case of wire, if our wire feed rate is very slow, we can have a dripping type of deposition, which again is undesirable. So this has to be optimum. Studies have suggested that lower particle velocity for an increased catchment efficiency are good. So this can be low. Of course, when I say low, I do not mean arbitrarily low. There is of course some floor which we should maintain, but they can be reduced significantly without affecting the process parameters too much. While the particle velocity will also affect the deposition rate, what we can have is we can have slower particles, but more particles per unit time. So we compensate by say either increasing the channel cross section or by then packing them more densely. For feedstock selection, reflective materials such as aluminum and copper are difficult to process using conventional IR lasers as compared to shorter wavelength lasers. Also, typically you would have heard that for deposition of copper, these days blue lasers are preferred. The melt pool size for conductive materials such as copper, because of the very high thermal conductivity, are fairly small, thus necessitating a smaller focal point of powder streams. Irrespective of the powers you give, often for copper, you'll find that the melt pools are very small, and it is only when for this typical uh, close to 1000 nanometer wavelength lasers, it is only when you go to powers in excess of 2 kilowatts, say 2.5 or 3 kilowatts, is that when you can even have some say acceptable deposition. And even in those cases, the melt pools tend to be very short because the heat is deposited, the heat is taken away so fast, it is dissipated so quickly. It is very difficult to induce localized heating, which may promote melting in a small region and thus the formation of a melt pool. In terms of stream characteristics, at the focal spot, water particle concentration often follows a Gaussian trend, which implies the validity of the 1 by E square rule. Ideally, the spot size of the powder stream should be smaller than the melt pool dimension to ensure high catchment efficiency, as we just saw. For the shield gas, its primary job is to prevent melt pool oxidation. In powder-based or blown powder processes, it also carries the powder. Again, a third function can be the protection of laser optics from the metallic fumes and powder particles. And typically, you want to keep a high enough shield gas flow rate unless it starts interfering with your deposition by affecting the free surface of the melt pool. Omnidirectionality is a very important consideration, and lateral feed nozzles are non-omnidirectional. Thus, they're used only for very simple applications, such as the cladding of rotary components, such as we looked at last week. Vacuum nozzles will typically be omnidirectional and thus employed for your typical part fabrication. Some concepts of or prototypes of smart powder delivery nozzles are also have been described, and they require a closed-loop feedback control with multiple inputs to adjust the feed parameters in real time in accordance with those of the system. And especially for compatibility with electron beam based systems, which will require a vacuum environment, carrier gases may need to be avoided, and this necessitates the development of gas free powder delivery nozzles. Here, some popular powder feed based machines are also described. So, here you have the systems developed by Optomec. They have powers ranging from 400 to 3000 watts, and the melt pool diameter is between 3 to 0.3 to 5 mm. Spot size is of 0.67 mm. The deposition head can come with either a continuous or a discrete nozzle with gas delivery systems, and 4-tip powder feeder. So it allows good control over the material combination and composition as well. The deposition rates can be as high as 500 grams per hour, or almost at 600 gram per hour is 60 minutes. So 10 gram per minute. And the systems can have either an open or a controlled atmosphere, and they can make hybrid and standalone additive manufacturing systems. A hybrid one is, of course, as we know, one which has both additive and subtractive capabilities. Some machines by DMG Mori are also showcased here, and these typically have powers in the range of 2.5 to 3 kilowatts, and they use a diode laser. The spot diameter in this case is larger, anywhere between 1.2 to 3.6 mm. In this case, the laser head is integrated to the headstock. The deposition head is a continuous coaxial type. Build rates can be far higher at 2 kgs per hour, whereas previously it was up to 0.5 kg per hour. The particle size can be between 45 and 120 microns. The next system is by Beam, which is a French company. And here the powers can be as high as 4 kilowatts. And depending on the model, the nozzle size, the build rate, the deposition width, and other things can change. And these can have also pretty large build envelopes depending on the model. Lastly, we have this example of a robotic arm, which is from an Italian group. And here they used a 3 kilowatt laser with 1070 nanometers, so pretty close to your usual 1000 nanometer, and a focal length of 200 mm and a spot diameter of 1.4 mm. Also, one very interesting way to realize duct-like features or prismatic but hollow features has been described here, where you first build the structure, the hollow walls, and then when you have to deposit this top face, which is clearly an overhang, you fill the hollow structure with powder of the same material, and then you run a defocused pass to center this powder. So what we can do is either we can defocus the beam by changing the standoff distance, or we can keep it focused, but we can decrease the power. This will consume more time, but either will have the same impact. That is, it will center the powder in say a few layers from the top. So up to a small thickness, the powder will be sintered, and then this can act as support for the top face that has to be built. And Slanger in the year 2000 has effectively demonstrated this technique for building of such duct-like structures. Next, we'll talk about again powder AM, but some modeling of the powder feed AM processes in terms of the process parameters. We'll also define the catchment efficiency and the bead profile. And then we'll look at its applications for large scale parts, for FGMs, for surface cladding, for repair, and for something called grid stiffened structures. As we already saw, laser cladding was perhaps one of the first processes which uh, described AM-like features and was typically used for, uh, say, strengthening the surface in terms of hardness and wear resistance, and also maybe to make it more resistant to corrosion by coating it with a different material. Now, this was the original design, which had a lateral feeding nozzle, but later this design was modified into the one shown on the right, where now you have the coaxial nozzle, whether it is continuous or discrete, I'm not sure, maybe it's a continuous coaxial type, and you have the laser coming centrally. And here we have a formal definition of the catchment efficiency. It is defined as the ratio of the mass of clad layer to the mass of powder ejected from the nozzle and multiplied by 100 for the percentage. And for the simple case of side feeding lateral nozzle, we have also derived a very simple expression for this catchment efficiency. And this can be defined in this case as the area of the molten pool AM by the area of the powder striking the substrate. And here we have assumed that, just like the case we discussed, to maintain normal directionality, the projection of the powder on the substrate is larger than the beam spot size. Now, if we assume uniform distribution of powder in the projected area, typically you would assume a Gaussian-like distribution, but just for the sake of simplicity, it has been assumed constant. Then the area of the powder striking the substrate, as we can see here, is B cross C cross pi by 4 or pi by 4 AB because it's an ellipse, which gives us this expression pi dp square by 4 cos theta. dp here is the diameter of this powder stream. Because of the inclination between the powder stream and the substrate, the profile that we get on the substrate itself is elliptical rather than being circular. So here also this will be dp. and because of the inclination, the length that we get C turns out to be d by cos theta, whereas the dimension B remains as dp. That is also reflected here, so pi by 4 AB. So that becomes pi by 4 times dp cross dp by cos theta. The size of the melt pool can be approximated by Rosenthal's equation for a moving point source, and the equation is given here. T minus T naught is P naught by 4 pi k exponential minus V xi by 2 alpha exponential minus Vr by 2 alpha, where T is the temperature at any distance r, T naught is the ambient temperature, alpha is thermal diffusivity, V is travel speed millimeter per second, chi is x minus pt is the distance along the traverse direction, and r is the radius of the melt pool. P naught is the absorbed power and k is the thermal conductivity. Now, in the moving coordinate system, that is, if we were to sit on the laser itself and travel with it, the temperature profile will simply be T minus T naught equals P naught by 4 pi k exponential minus Vr by 2 alpha, because now zeta becomes 0. Sorry, xi becomes 0. And so now we have to obtain the portion where the temperature will be more than or equal to the melting temperature, or simply we want to look at the region enclosed by the liquidus isotherm. If we were to substitute the value of the melting temperature Tm into this equation instead of T, we can find the expression for R, which describes this region. So now here the region less than R gives the temperature greater than the melting point. This can be further uh, simplified using a Taylor expansion for exponential minus Vr by 2 alpha and neglecting all terms other than 1. So typically this would have other terms like 1. The Taylor expansion is so 1 minus x plus x square by 2 factorial minus x cube by 3 factorial plus x4 by 4 factorial and so on. But we discard all terms other than 1. We just equate the LHS to 1 and then come up with a very simple expression for R. And if you assume uniform density intensity distribution of the beam projected on the substrate, again in a more realistic scenario, this may be Gaussian or it may even have any other type of distribution based on the beam profile that you are working with. The area for the beam can be calculated as shown here, and then we divide the area for the laser spot size by the area of the uh, projected powder stream, and we come up with an expression for the catchment efficiency. Eta is equal to P naught square cos theta by 4 pi square dp square k square Tm minus T naught square into 100. And there is a simple example here. So in a powder feed based AM process, an off-axis nozzle is used to feed material into the molten pool. If with the same setup and laser power, the material is changed from A to B, and the melting point of material A and B are same, but the thermal conductivity of material B is 4 times higher than thermal conductivity of material A, find out the ratio of the catchment efficiencies of both the materials. So we are told that the melting point of material A and material B are the same, the thermal conductivities are different, and the other process parameters remain the same. For one material, we have, say, eta A is equal to, assuming the process parameter are the same, P naught square, the inclination remains the same, cos theta, 4 pi square, dp square, Ka, because they are different square. The melting point for both the materials is also same. So Tm minus T naught square, T naught being the ambient temperature into 100. For the other material, P naught is same, the inclination theta is same, the diameter of this powder stream or the laser, the powder stream profile is the same, so dp square. The thermoconductivity is different, so we give a different subscript kb square. Melting point is again the same, so again T naught, ambient temperature is the same in 200. And we have to find the ratio of the catchment efficiencies for both the materials. So when we divide eta A by eta B, all the other terms are lost. The only terms which survive are Ka square and Ab square, which are also shown here. Further, we know that the thermal conductivity of material B, Kb, is 4 times higher than the thermal conductivity of material is Ka. So we have 4 Ka whole square by Ka square, 16 by 1 half, 16, which is also shown here. The catchment efficiency has also been explicitly calculated for us a simple case. So in a powder feed nozzle based AM system, the steel metal powder is injected using an off-axis nozzle at an angle of 60 degrees from the horizontal through a nozzle of diameter 5 meters. If the nozzle power is 1 kilowatt, find out the catchment efficiency of the process. It has also been calculated here, so I'm not repeating the exercise. Now here we see that the interaction of this powder stream and the laser beam can be divided into these different zones. So here, if at an intermediate position, if we were to take a cross section, what we'll find is that the powder is coming in this donut-like shape, assuming a continuous coaxial nozzle for the powder delivery, and the laser beam is in the middle. The laser is not really interacting with the powder. Now, in region 2, so somewhere over here, the powder stream is not donut-like or annular anymore. It is now a circle, and the laser beam. I'll just also highlight the powder particles in this region for easier visualization. Here, the powders are everywhere, including in the center, and the laser beam spot size will not change by a lot. It is somewhat smaller, but it's still at the center. So now the laser beam is interacting with the powder. In region 3, or somewhere over here, the laser has already reached its base radius and now it will diverge, and the powder stream will also diverge. So now you have a larger powder stream. It is not annular, so the powder is available everywhere. And now the laser will also start diverging, so maybe it is larger than before. But both the laser and the powder stream reach their minimum. Powder stream reaches its waist at this section AB, and the laser reaches its minimum at this distance that is shown as FL. So depending on the region we are, whether it is in region 1, in region 2 or region 3, and at the intersection of these respective regions, the interaction between the laser and the powder will be different. Now typically, powder delivery nozzles also follow a Gaussian distribution of powder particles in 2D space, on a 2D surface or a 2D plane. The rule states that the powder stream's spot radius at the focal or convergence plane is determined by the location at which the particle density is 1 by E square of the maximum. So this is your typical definition of the diameter radius of a Gaussian intensity distribution. We know that there it goes on till infinity, but at a region of around 1 point E square, some 95% of the in this case particles, or in some case energy, may be stored. Therefore, the particle number concentration at any point xy in a plane which is characterized by A here, the subscript A, in the cross section in a slice will be given by Na at a position xy is equal to n naught e to the power minus r square by k, where k is a constant. N naught is the peak particle number concentration at the stream center, and if r is the boundary radius at which the particle density is 1 by e square, the maximum, then we can plug in this value, that is at small r equal to capital R, Na will simply equal n naught by e square, which equals n naught exponential minus r square by k. And thus we can simplify it to the given expression. Na at xy is equal to n naught exponential minus 2r square by capital R square. However, n naught is still unknown. But what we can know is the total number of particles in the region, and we can correlate the two. So if we want to find the total number of particles in the strip, we can find the number of particles in a small ring-like or strip-like region at a distance r and a thickness dr, and integrate it from 0 to infinity, because remember, because of the asymptotic nature of this Gaussian distribution, it is expected that even at infinity there might be some powder particles present. 95% of them will be within the radius of 1 by e square, but even at infinity some particles may still be present. And then we can come up with an expression which gives us that relates n naught and np, and n naught is equal to 2 np by pi r square. Thus, this yields the final expression. The particle density, the number of particles at any point xy in a slice which is at a height a, is given by 2 np by pi r square exponential minus 2r square by r square, where np is the total number of particles in that slice, r is the radius characterized by 1 by e square, and small r is the distance at which we are looking. Now, the particle number concentration at a height in region 2 and region 3 can be given by the Gaussian function. In region 1, it cannot be because of the annular nature of the powder stream. Na at any distance xy is equal to 2 np by pi r z square. So r is a function of z in this case, as we see, depending on whether we are in region 1, 2 or 3 and how z is changing. Also, for the sake of reference, here z is assumed 0 here and it is positive downwards. So as we are moving along the z direction, the value of this radius will change. So z is the powder defocusing distance, rz is the powder flow radius reaching 1 by e square of the peak powder concentration, when the powder defocusing distance is z, taking the powder focus point as origin. Now, assuming the effect of powder gravity is neglected, the powder flow radius can then be expressed in region 2 as r as a function of z is equal to rp minus z cot alpha. In region 3, it is rz is equal to rp plus z tan beta, and rp itself is given as r naught minus fp cot alpha. So maybe we can look up how these expressions are coming. So for the case of say in region 2, so somewhere here, rp is this radius, z is the distance we are going back, and alpha is this angle. Okay, maybe RP is not illustrated here, but we can refer to the videos in which Professor Kapil has described excellently how each of these expressions are derived. Now, as a further simplification, we can assume that the upper surface of the molten pool is a circle. So we are looking from the top on the deposition plane. and the melt pool has an exactly circular shape, which we know is not typically true. Typically, with the direction of laser travel, it will have this oblong-like shape, say if the laser is centered somewhere here. However, with this simple assumption, this upper surface of the molten pool can be given by the expression x square plus y square is equal to w by 2 square, and the primary efficiency of the powder can be expressed as a ratio of the quantity of deposited powder to that of the total fed powder. And since only the particles trapped in the pool are deposited, given that the pool surface is shaped as a circle, the primary efficiency of the powder, eta P, can be expressed as double integral NaXy ds by Np, and when it is further simplified over that circle, so for this circular region, as I'm moving out from the center, say at some distance r at an angle theta, we are taking a section. Okay, maybe I can draw this a little bigger for easier visualization. At some angle theta, we take an element which is d theta thick and dr wide. So this dimension is dr and this dimension is d theta, and then we integrate it as r going from 0 to w by 2. So and theta going from 0 to 2 pi. And upon doing this, we end up with the expression of eta p is equal to 1 minus exponential minus w square by 2r z square. And what can be seen from this is that the primary efficiency of powder is a function of the melt pool radius and the powder flow radius. It is dependent on an exponential function involving the ratio of melt pool radius to the powder flow radius. Of course, this has been performed for a melt pool shape assumed circular, which will not generally be the case. The mass formation speed, or say the speed or the rate at which the bead is getting deposited, can then be expressed as the mass flow rate MP into the primary efficiency eta P. So Min is equal to MP times 1 minus exponential minus W square by 2R Z square. Some particles will also bounce out of the molten pool, and let us assume that eta U is the powder utilization rate. So we multiply this with the other factor eta U to come up with the final expression. And this will happen because the particles are traveling at such high velocities, they can simply interact or collide with the melt pool, and rather than getting assimilated into it, can simply bounce off. And typically, when we are visualizing a powder DD process or seeing a video of a powder DD process, we see many sparks flying out, and it is actually these powder particles which are bouncing away from the surface that we see. Now, while the top of the melt pool was assumed circular, now that we are moving the heat source and the bead is getting deposited, if along the cross section we assume a parabolic shape of the deposited bead, the bead cross section can then be described by the equation given here. Z prime is equal to minus 4 by 4h by w square y prime square plus h for all reasons where z prime is greater than or equal to 0, that is above the substrate, where w is the width of the track, h is the height of the track. And then we can have an expression for ms, which is 2/3 Vs Wh rho. This ms should be equal to the mass building So ms is the min is the mass formation speed, and ms is okay. Ms is maybe the amount of is the mass flow rate from the stream. Both of these should be equal because we already taken the catchment efficiency into account. And this gives us the height of the deposited bead as 3 mp eta u 1 minus exponential minus w square by 2 rz square by 2 w vs rho. And one can find the width of the molten pool by approximately considering the Rosenthal equation for a point of surface heat source as the need may be. One can also obtain the value of height of the bead. You may obtain the width of the bead from the above equation. So similar to our previous case, we can see that again for the purpose of maintaining a flat surface between two successive beads in the same plane, we can come up with an expression for the optimum step over distance based on some geometric assumptions. And it turns out that in this case also, the optimum step over P is equal to 2/3 times the width of a single bead. So P is equal to 2/3 W. Now, another important consideration in these laser cladding like processes, such as powder feed based DIM or laser wiring, is the dilution ratio alpha. And here the dilution ratio is defined as delta by beta plus delta. Delta is the amount of or the depth of the melt pool. So if this is a melt pool, some of it is also below the surface. So delta is the depth of the melt pool below the surface, and peak depth, so to say, measured near the center of the melt pool. Beta is the height of the melt pool above the substrate, and the dilution ratio alpha itself is defined as delta by beta plus delta into 100. The optimal range for dilution ratio between the first layer and the substrate lies between 10 to 30%. If we have a dilution greater than 30%, it may be indicative of a keyhole mode deposition regime where the melt pools are very deep and you may end up disturbing or destroying previously deposited features, or porosities may end up getting trapped. If the if the dilution ratio is less than 10%, you may have a lack of fusion where the metallurgical bonding between the deposited bead and the substrate is not proper. The bead may have very poor strength, and also there may be a total lack of fusion between them. That is, there may be a crack or a large void between the deposited bead and the substrate. And a parameter often used to monitor for these either keyhole regime or lack of fusion regime is a global energy density defined as P by Vs into dl, where P is the power, Vs is the scanning speed or traverse speed, and dl is the diameter of the laser spot size. The global energy density is used to investigate the interlayer and intralayer porosity due to the lack of fusion or keyhole. The region with low global energy density are subjected to lack of fusion-induced porosity, and the region with high global energy density have the chances of keyhole porosities. Now, for the case of powder feed-based additive manufacturing processes, the defects such as residual stresses, porosity, and crack and delamination are often the same as discussed for TIG, MIG-WORM based processes. Powder feed-based DAD finds use in some very interesting applications, such as in feature addition and for large-scale components. Powder feed-based AM can be used for manufacturing of large-scale components, such as the Lens 850R system by Optomec, which has an exceptionally large work envelope of 900 cross 1500 cross 900 mm to build or repair large volume components such as blisks, impellers, and shafts. Features can also be added on pre-built parts. using feed-based AM. Further, challenges like cladding or feature addition on internal or difficult to access locations can be addressed by appropriate design of the cladding head. Powder feed-based AM can also be used for making functionally graded materials, which are objects whose properties are designed to vary in different parts of the product, such as the local properties of the material in a part are suitable for the design function. Now they can have variations based on densities, based on material, or based on color, or they can have, depending on the gradient, whether it is a stepwise gradient, if you have these regions of continuous characteristics, say be it composition or density or texture or whatever. And then you have a sharp change over a very small region. Those are called stepwise gradients. Or you can have a continuous gradient based on any function such as a linear function or any other monotonely increasing or decreasing function, which will have a continuous change in the functionality. FGMs are characterized by gradual transitions in either composition constituent or the microstructure, which may be described in terms of the grain size, the texture, or the porosity, along at least one direction. It can happen in more, leading to functional changes associated with at least one property. Obtaining FGMs across the build direction is far more challenging than FGMs along the build direction, as we just discussed. These can also be used for laser cladding and surface alloying applications. And laser cladding or alloying is a process that attempts to modify the properties of the base material surface using a similar or dissimilar material by melting both in order to obtain a new surface with desired properties of corrosion and wear resistance and augmented hardness. It can have applications such as in shafts, rods, and seals, in wall parts, sliding walls and discs, in cylinders and rolls, in turbine components, for sealing joints and joint surfaces, and in tools, blades, and other molds. Powder-based DAD can also be used for part restoration and repair. And we have an example of a turbine blade here, which was manufactured from powder feed-based DAD process. Then during service, uh, it got damaged and a part of it was lost. And rather than replacing the whole turbine blade, only the damaged part was repaired by further powder-based DD process, and then it could be put to use again. So for repairing purpose, the component is digitized and transformed into a mesh representation. This provides the CAD input which can later be analyzed for extracting the repair volume and toolpath planning. The ability to repair the components increases the tool life, reduces cost of operation, and promotes design freedom. An upcoming application is those of that of grid stiffened structures. So your grid stiffened structures are conventional plate and shell members backed by these repetitive patterns of ribs laid out in a specific geometric configuration. Grid stiffened structures are popular due to their high load carrying capacity with minimal structural weight, or in other terms, high strength to weight ratio. This is a term that is thrown around a lot. Typically, titanium is a material with very high strength to weight ratio. Now, these structures prevent local flutter, they absorb vibrations, and they possess high bending stiffness while providing convenient mounting points for other structural members and machine components. Finally, to summarize, here are the advantages and disadvantages of powder feed based AM processes. They can have very high deposition rates of the order of 3 kg per hour. There is a possibility of realizing material or composition based FGMs. They can be used for part restoration and repair. They can be used for laser cladding applications, and they can be used for in situ processes. In terms of disadvantages, we still cannot have explicit support mechanisms. The layer thickness is on the higher side, which leads to bad surface finish and a lack of processing or building tiny parts. And the catchment efficiency will often be pretty low because of the powder stream divergence and the high velocity of powder. That brings us to the end of the review for the concepts discussed in this week. Now we'll take a short break, and when we return, we'll discuss some uh, example questions that will help us solve assignments. We'll just take a short break. Welcome back to the live session. Let us now look at a few exemplary problems which will help us clarify our concepts and solve the assignment questions for this week. So this first question is similar to what we already solved. Now for the second question. In a powder feed-based AM process, an off-axis nozzle is used to feed material into the molten pool. If the power of the laser is decreased to half the original power, what will be the corresponding change in the catchment efficiencies? So if you remember, the expression was derived for this exact case, and I will just write the expression. So for the catchment efficiency eta, it was directly proportional to P naught square cos theta by dp square k square tm minus t naught whole square. And in this case, we are told that the power of the laser is decreased to half the original power. So we have two scenarios. For scenario 1, the power was P naught. In the second scenario, the power was decreased to half the original power. So we had to find the corresponding change in the catchment efficiency. So if we were to denote the efficiency, catchment efficiency for the first case as eta 1, this is proportional to P1 square. This is P2. P1 square cos theta, because the inclination remained the same, dp square. The diameter of the powder stream remained the same, some conductivity as well, and the temperature ranges. And eta 2 is proportional to P2 square cos theta by dp square k square tm minus t naught whole square. Now, if you have to find the change in the catchment efficiency, we can see that all the other factors remain constant. It is only the power that is changing. So we can come up with an expression in terms of ratios. Eta 2 by eta 1 shall equal P2 square by P1 square, because all the other factors are getting cancelled out. This implies that eta 2 by eta 1 is equal to P2 is P naught by 2 and P1 is P naught itself. So 1 by 4, and therefore for the second scenario the efficiency is equal to 0.25 times the first. So by decreasing the power to half, we see that the catchment efficiency has decreased to 25% of the original catchment efficiency. For the next question, in a powder feed-based AM process, an off-axis nozzle is used to feed material into the molten pool. So the case which has been modeled in the class, if the diameter of the nozzle injecting the powder is 8 mm and the injection angle is 45 degrees, so we have values for phi, or is it theta, and dp is 8 mm. Theta is 45 degree, which is pi by 4. Find out the projected area of powder on the horizontal plane. And so, just to recollect, this is the flat substrate, and the powder is being fed from the side, and we have this diameter, which is dp, and we have the angle with the vertical axis and the powder delivery tube. So this angle is given to us as pi by 4. And as we saw during class, While the powder stream itself may have a circular cross section, because of the relative angle between the substrate and the powder stream, its projection its projection onto the substrate will be elliptical. And while the one dimension continues to be equal to dp, the other dimension is elongated, and this as we saw is dpy cos theta. For the ellipse, we know that the area is equal to, say, if you have an ellipse with the major axis as A and the minor axis as B, the area is pi by 4 AB. In this case, the area turns out to be pi by 4 dp by cos theta times dp, or pi by 4 dp square by cos theta. So we'll just compute the values for this scenario. So here the dp is 8 mm and theta is given to us as pi by 4. And if you plug it into this expression, AP, or the area of the projected power stream, is pi by 4 times dp square by cos theta, which is equal to pi by 4 times 8 square by cos of pi by 4. And if I were to just calculate this quickly, so this comes out to be 71.086. The dimension of dp was in mm, so mm square. And this is the projected area of the powder on the horizontal plane. In question number 4, we are asked, in a powder feed-based AM process, if the power of the laser is decreased to half the original power while increasing the scanning speed to double the original speed, what will be the corresponding change in the global energy density? And just to recollect, this global energy density is the parameter which is used to judge whether, say, some region of the print is subjected to very low dilution and may result in lack of fusion type defect, or is subjected to very high dilution, which may lead to a keyhole type defect, a keyhole induced porosity. And this GED was expressed as P by Vs times dl, where the P is the power, Vs is the scanning speed, and dl was the laser spot size. Now we are given two scenarios. Let originally, okay, suppose originally let the power be equal to P itself, the scan speed be equal to Vs, and the laser spot size be equal to dl. This is a nominal case. Now in case 1, power of the laser is decreased to half an power while increasing the scanning speed to double the vision speed. So things remain the same. We have P, Vs, and dl. In the second case, power of the laser is decreased to half. So, okay, just for sake of clarity, I'll write them with subscripts so that while putting it in the expression, we can do easily. So P1 is equal to P, V1 is equal to Vs, and D1 is equal to original DL. P2 is equal to half the original power. So V2 is equal to, increasing the scanning speed to double the original speed, so twice Vs, whereas there is no comment on the laser spot size, so it remains unchanged. We are supposed to compute the corresponding change in the global energy density. So for the first case, GED is equal to P1 by V1 D1, which is equal to P by Vs dl. For the second case, is equal to P2 by V2 D2, which is equal to P by 2 by twice Vs times dl equal to P by Vs dl by 4. And if we are to compare the global energy density for either case, GED1 or say GED2 by GED1, we see that this is P by 4 Vs dl by P by Vs dl or 1 by 4. So we see that by halving the power and by uh, making the doubling the scanning speed, we see that the global energy density has decreased to one-fourth of the original case. And because of such a low global energy density, we may expect that the regions may be exposed to lack of fusion type of porosity. So we should be very careful while changing the process parameters, as most of them are interconnected and cannot be changed arbitrarily, and changing them without proper thought may lead to such defects. Question 5 is asking us, which AM process is the most suitable for repair of damaged components such as shafts and turbine blades? So during the discussions, we saw how there was this, say, turbine blade. Typically, it has a geometry like this, but we saw that it got damaged. So somewhere over here near the top, and how it was repaired again and then put back into service. We are being asked which AM process is the most suitable for repair of damaged components such as shafts and turbine blades. Is it binder jetting? If you remember, in binder jetting like processes, we had this this vat where which was filled with powder, and for each layer, binder was jetted onto it in the form of these droplets, and wherever the binder fell, the powders got cured selectively and formed the part. Now, in this case, while metallic powder binder jetting is our developed technology, still we see that for repairing this part or for repairing a large part such as a shaft, we will have to say cover it by this binder powder, and even the motion of the roller or the doctor blade can collide with this part. So say initially I would want to have powder till here, then I'll have to spread powder till here and so on. And in this case, there's a very high chance that the roller or the doctor blade will in fact collide with the part, and I will not be able to repair or build this part again. So binder jetting is out. Is it powder bed fusion? Now powder bed fusion again presents similar complications. The dynamics are different, but the process more or less remains the same. Is it sheet lamination? In sheet lamination, if we recollect, um, the part is built sheet by sheet, and then based on the contour lines and the grid lines, the unnecessary regions are removed, and the final part is exposed. But here again, it cannot really be used for repair because we cannot mount sheets on top of this one. So the only remaining and the actually practically used application or process is the direct energy deposition. And this is also something we discussed in the lecture. Now, additive manufacturing allows the manufacturing of functionally graded materials. Some factors related to the process are listed below. Formation of secondary phases and intermetallics during formation of FGMs. Dilution, that is the deviation of actual chemical composition from the design composition. So this dilution is different from the dilution ratio alpha that we saw. This has more to do with the deviation in the chemical composition from the actual intended or designed value. Like we discussed how it can be a stepwise gradient in composition or it can be a continuous gradient. But what if the actual gradient is not really as steep but varies not as per design, or say it is almost flat and then it saturates. So that's the type of dilution being discussed here. Thermal property mismatch, that is mismatch of coefficient of thermal expansion between the two parts, between various regions, and residual stresses. Which of the above factors should be considered while choosing material combinations for FGMs? Now, if it is a material based FGM, that is, there are different materials which are being combined to form an FGM. If they are not metallurgically compatible, or if from the binary phase diagram, we see that there are regions in which some deleterious secondary phases form. Uh, we should be careful in the choice of such materials because then the combination of these materials will lead to these brittle phases, which may contribute to the overall failure of the system. So, the formation of secondary phases and intermetallics, or that is the metallurgical compatibility, is definitely something worth looking into. Dilution or deviation of actual chemical composition from the design composition is very important because these FGMs may also be used for some very strategic applications, such as, say, in implants, where you might want to vary the density as per the natural density variation of bones. And if there is any deviation from the design values, it might have unintended consequences. Similarly, for a material or composition based FGMs, you may be using it for a very targeted application. Say in one region, you want high thermal conductivity, whereas in the outer region, in the jacket, you want good structural strength. If these properties are not retained, then the final application cannot be met. Thermal property mismatch, such as say if you're having stepwise gradients and I'm depositing one material on top of the next, and if there is a large mismatch in the thermal uh, properties, such as the coefficient of thermal expansion or the thermal conductivity, then at this interface, because of the large residual stresses, we can expect that the material will fail and they might get delaminated or cracking may occur. And I've also seen very nice videos where these residual stresses are shown to just spring this material away almost in an explosive fashion because of the very large mismatch in thermal properties. And residual stresses, as we saw, can lead to cracking. So all of these factors are very important considerations when we are um, selecting materials for building an FGM. Also, there's an interesting material called Invar. So it's a nickel alloy, and its coefficient of thermal expansion is almost zero. It's of the order of, if I remember correctly, 10 to the power minus 6 or so. And so basically, it does not undergo any thermal expansion. So it's uh, really interesting to work with. Question 7 is asking us, for powder-based AM processes, which technique of powder processing produces the finest quality powders in terms of morphology and quality? So this might not be something that was discussed during the lectures, but it always helps to know a little about these things and how the powder was manufactured. We take it as ready feedstock for our processes, but if we have awareness about the manufacturing process, this may help us to make informed decisions. So let us look at the types of powders that are created from each of these processes. For powders that are created by water atomization, that is, a jet of water is used to break uh, the molten metal into small droplets, which then solidify into the powder particles. The particles do not tend to be spherical. I mean, the sphericity is low and they tend to have these random oblong shapes. For gas atomized particles, while the control over the shape or morphology is better, because of the entrapment of gases, they can have these pores in them. Also, because of the entrapment of gases, the chemical composition might be different because now these gases are also trapped. And even the sphericity, while better than the water atomized particles, is not perfect. Whereas for the case of, say, plasma atomized particles, the particles have very good sphericity as well as they are defect free. So, if we are given a choice, of course, depending on the powder characteristics, the cost also shoots up. So, water atomized powder will be cheaper than gas atomized powder, which in turn will be cheaper than plasma atomized powder. But if we are to compare them in terms of the morphology and powder quality, plasma atomized process, plasma atomized powders tend to be superior. Question 8 is asking us, a functionally graded material can have variation in which of the following properties? Is it density, like the human bone, which is soft in and also hollow in the center, and very dense and hard on the outside, and the density changes progressively as we move radially outwards? Is it the chemical composition? Many examples of which we saw during our discussions. One I can recollect is that of copper and tool steel. Is it of color? And we saw some color-based FGMs during our initial discussions, uh, where small transparent parts or translucent parts were made with different colors. Those colors were not just on the surface, but all the way through. And in fact, FGMs can have variation in all of these properties. And there can be many others, such as magnetic properties, whether they are ferromagnetic, paramagnetic, or non-magnetic. It can be in terms of, say, hardness or in terms of microstructural features such as texture, grain size, as long as it suits a functionalized process or a functionalized objective, the material may be admitted as an FGM. So that is all we had for today. We have also come to the end of our time slot. So thanks for tuning in. This was week 10 of the live sessions for the fundamentals of additive manufacturing technologies. I am Sourav Goswami from IIT Bombay, and it was good to have you. I look forward to interacting with you again next week.